Okay, welcome to my all of AS Maths Paper 1 for Cambridge. So if you're doing this particular course, the AS Maths Paper 1, and this is the video for you, either do a crash course in the next about 2.5 hours on the key topics that you need to know, or you want a refresher on the most important topics. And this is exactly what I do in the video. So I go through the top 10 topics that I have picked out from the paper 1, and to make sure that you're familiar with the exam style questions, and I'll go through 2 questions per topic so you're up to speed for the paper 1. Right, number 1 is binomial expansion. So being able to expand binomial, but also compare coefficients and use that to solve problems. So I'm going to look at 2 questions just now, going through exactly that.
Okay, and we're going to look at our very first topic here, which is binomial expansion, coming up pretty often on the paper 1. So first thing, question 1, find the term independent of x, I'll explain that in a moment, in the expansion of 2x plus 1 over 4x squared, all to the power of 6. So when they say the term independent of x, they mean just the constant term. So the term that's left, that's just a number, so nothing to do with x or x squared or x cubed, and so on. So what we're going to do here is actually expand this out, and then as we go through, let's see if we can find that constant term. So I'm just going to use the formula that you should be familiar with from this course, and I'm going to use the following notation here. So first of all, we need our binomial coefficient, so we're going to start with 6c0, and all we focus on is just the first term here, so 2x to the power of 6. Okay, that's not going to give us a term independent of x, which is unlucky. Let's just continue. So then we have 6c1, then we're going to have 2x to the power of 5, and then multiplied by one lot of this here. Now, just by looking at this, we're going to get a x to the power of 5 term here, an x squared term on the bottom. X to the power of 5 divided by x squared is x cubed. So this term wasn't going to work. This term won't work either. So let's just keep continuing. So we get 6c2, then we get 2x to the power of 4 multiplied by 1 over 4x squared to the power of 2. Remember these indices, so let's get that trusty highlighter out here. The 4 and a 2 has to add up to 6 here. 6 plus 0 is 6, and then 5 plus, well, there should be a 1 there. I'll put a highlight where there should be a 1. Again, this is how we check that we are getting the correct expansion. Now here, let's just have a think about this. If I square this, then 2 times 2 is 4, so I get x to the power of 4 at the bottom. There is an x to the power of 4 here. That's going to cancel and give me my term independent of x. So actually, this is the term that I am going to focus on. Now, if you don't believe me at this point, then please do keep watching and you'll see the x's will disappear. So we're going to have 6c2, and now 2x to the power of 4 multiplied by 1 over 4x squared to the power of 2. So let's work out this part first of all. 2 to the power of 4 is equal to 16. X to the power of 4 is x to the power of 4. If we square this, then we need to square both top and bottom. So 1 stays the same. 1 squared is 1. 4 squared is equal to 16. And x squared all to the power of 2, that's equal to x to the power of 4. And now we need to work out 6 choose 2. Now you can do this on your calculator. I'm going to show you where that is. The way we're going to do this is we're going to type in 6. I'm going to type in C, and then we type in 2, and that will generate the binomial coefficient. Again, on other calculators, this might be a little bit easier, but we get 15 here. So let's pop across 15 for here. And notice that we get a cancellation here and here. Notice everything cancels, leaving us just with 15, which is our answer. So this is a very nice cancellation because you get the same thing top and bottom, so giving you 15 as your answer. Right, so you can check the mark scheme there, and they've done it maybe slightly differently to how you've seen in the mark scheme here. Now let's look at a slightly trickier question. So question 5, in the expansion of 2x squared plus a over x to the power of 6, the coefficients, so the number in front of the x squared and the x cubed, are equal, and we need to find the value of the non-zero constant a. So a we can't assume to be 0, otherwise life would be too easy. So the first thing I'm going to do here is I'm going to start writing out my expansion, and let's see when we get our x to the power of 6 term and x to the power of 3 terms. So we get a over x to the power of 6, and this is approximately equal to 6 choose 0, just using the formula here. So 2x squared to the power of 6. Okay, that's not going to be a term that works because we get x to the power of 12. So let's keep going through. So 6 choose 1. 2x squared to the power of 5 plus a over x to the power of 1. Let's think about this term here where we get a x to the power of 10 here and x at the bottom. So x to the power of 10 divided by x is x to the power of 9, so that's not going to work. Let's look at our next term. 6 choose 2, 2x squared to the power of 4, should be a multiplied there, sorry, multiplied by a over x, all squared. Let's think about this. So we get 2 times 4 is 8. 8 divided by x squared is 6. So that's going to give us our x to the power of 6 term. So we'll come back to that. And then 6 choose 3. 2x squared to the power of 3. A over x to the power of 3. Again, let's have a think about this one. So 2 times 3 is 6. So that's going to give us an x to the power of 6. Divided by x to the power of 3, that gives us an x cubed term. So these are the two that we actually need to look at here. Now 6 choose 2 we did in the previous question, that's equal to 15. That makes our life a little bit easier. Okay, 2 to the power of 4, that's equal to 16. X squared all to the power of 4 is equal to x to the power of 8. And then we get a squared over x squared. And in a moment, we're just going to simplify this down. So we get 16 times 15, that's equal to 240. So we get 240 a squared. These two things cancel, so x to the power of 8 divided by x squared gives us the x to the power of 6. So once we've worked out the second term, we're going to focus on that coefficient, which is the number in front of the x to the power of 6. Now let's look at this one here. 6 choose 3. We're going to go back to that calculator and work it out. Okay, so let's do that. So we get 6 choose 3, and that's equal to 20. So we're going to pop over 20 for that. So 20 multiplied by, well, 2 cubed is equal to 8. So we get 8x to the power of 6. And then we get a cubed over x cubed. And let's see what we're left with. So 8 times 20 is 160. So we get 160 a cubed, and x to the power of 6 divided by x to the power of 3 is x to the power of 3, which is what we wanted. So these two coefficients we're going to be looking at. So then we get our coefficient here highlighted, and because they are equal to each other, that's what we're told in the question, therefore 240 a squared is equal to 160 a cubed. Okay, we get some cancellation on both sides here. So we get 240 equal to 160a. Therefore, a is equal to 240 over 160, which we can simplify down. And that gives us 3 over 2, which is very nice. So we get to our final answer of 3 over 2. And the last part of the question is it wants to work out the coefficient of x to the power of 6 in the expansion. So let's have a think about this in terms of the pattern going on. So this one here, we got an x to the power of 12. Here, even though we didn't include this, we got a x to the power of 9. So here we get 12, 9, 6, 3. And if we continue on that method, on that particular pattern, we'll see we keep going down in 3s here. And then if you think about, we're going to multiply this by 3. We're actually not going to get a term that has a coefficient in x. You're going to get a cancellation. Therefore here, this is why it's a 1-mark question. So use that to help you here. You're actually going to get no coefficient. So it's just going to be equal to 0. Right, you can check the mark scheme here. So you can have a look through and see the calculation given. And then for the last question, it's just that it's going to be equal to 0. Okay, hopefully you found that useful. And again, we're going to move on to the second topic in a moment.
Okay, and number 2 is working with quadratics, which is quite a broad topic, basically focusing on the discriminant, so using the discriminant really, really well, also working with solving quadratics and completing the square as well. So I'll go through 2 very typical questions here, questions from the last few years or so, going through exactly this topic. Okay, and on to our section on working with quadratics. Now this can come up in a variety of different forms, but what's common to most of these questions is the use of the discriminant, which I'll talk about a bit later on. So it's testing your understanding of using the discriminant and helping that with working out a quadratic. So let's get started. So a curve has equation y equals kx squared plus 2x minus k, let's underline here, and a line has equation y equals kx minus 2, and k is just a number, it's just a constant, and we need to find the set of values of k for which the curve and line do not intersect. Now, the way that we actually go about doing this is that we pretend they do intersect, so we make them equal to each other, and then we work through the algebra, so get a quadratic, and look for no real solutions, which is where our discriminant comes into play. So we first of all make these two things equal to each other. So kx squared plus 2x minus k is equal to kx minus 2. And now to get a quadratic that we can work with, we need to make the right-hand side 0. The way we do this is add 2 and minus kx on both sides. If we do this, well, kx squared stays the same. If we minus kx from both sides, we get 2 minus kx. And then we just bring the 2 over, so we get minus k plus 2 is equal to 0. This cancelling here, and this cancelling here. Now we have a quadratic that we can work with. We're now going to set this up where we're looking for no real solutions, i.e. they do not intersect. And if we want no real solutions, then we need to make sure the discriminant is b squared minus 4ac, which is really important, is less than 0. Now where do a, b and c come from? They come from the coefficients of the x squared, the x here, and then the constant term like so. So this is going to represent our a, this is going to represent our b, and this will represent our c. And now we just put it into this formula and then work through that algebra. So if we do that, we get 2 minus k all squared minus, well, 4 times a, which is k here, lots of minus k plus 2 is less than 0. And now it's an algebra exercise to get something that we can work with. So we expand the bracket, we get 4 minus 4k plus k squared, and then we get minus 4k multiplied by minus k plus 2 is less than 0. Now let's expand over here, so we get 4 minus 4k plus k squared. You need to be really good at expanding these double brackets quickly. Minus 4k times minus k, that's plus 4k squared. Minus 4k times plus 2 is minus 8k. Almost there with our quadratics. So 4k squared plus k squared is 5k squared. Minus 4k minus 8k is minus 12k. And don't forget our little plus 4 over here as well. Don't forget our constant term is less than 0. Now the way we actually go about solving a quadratic inequality is we solve it as if it were a normal inequality. So we're going to factorize into 2 brackets, a very important skill to know. Now because we've got 5k squared and 5 is prime, we know 5k must go here and k here, or the other way around. And now when you think about the factors of 4 that go in here that can generate minus 12, well, we haven't got too many choices here. We've got 1, 4, or the other way around, and then 2, 2. Again, you can play around with the numbers here to try and get to the answer. I can see here we get minus 2 and minus 2. Now if you check the cross terms, that's the thing you should always check here. So 5k times minus 2 is minus 10k, minus 2 times k is minus 2k, and minus 10k minus 2k is minus 12k. So this is the correct factorization. That means our critical values, so we're not solving this, we're just finding the critical values. K is going to be equal to 2, or it's going to be equal to 2 over 5. Now if I do a quick sketch of a quadratic, again, this is not going to be to scale by any means whatsoever. There's our 2/5 solution, there is our 2 solution. Let me put that in a slightly different colour. So this would be our 2/5, this would be our 2. And because we're less than 0, we want to consider the domain of values below the line, so this part here. So then to write our final solution, I'll do this in black here, we get 2/5 is less than k, which is less than 2. Remember, it's going to be strictly less than because our inequality here is also strictly less than, and we want everything below the x-axis here. Okay, if you need to practice those skills, quadratic inequalities, that is a fundamental part of the course. So you can check out the answer here. So this is the final answer, which I got as well, and the corresponding working you need to get all 5 marks. Now my second example question is a little bit different. So we're going to use a bit of completing the square for the first part, and we want to express 16x squared minus 24x plus 10 in this form. So the way I tend to do these problems is I ignore the plus 10 for the moment. I will come back to that at the end. And I think, right, I want to generate this 16x squared minus 24x. So we're told in the question this needs to be a 4x. And then we need to kind of think backwards and think, okay, what number needs to go in here such that when I expand, I get a minus 24x. Okay, well, if I put a minus 3 here, for example, then 4x times minus 3 is minus 12x. I've got 2 lots of that, will give me minus 24x. Now, if you didn't get that part, that's absolutely fine. Let me just show you this by expanding this out in full. So if I expand out 4x minus 3 all squared in full, well, 4x times 4x is 16x squared, that's what we wanted. 4x times minus 3 is minus 12x, the same in the middle as well. And then minus 3 times minus 3 is equal to positive 9. If I collect up those middle terms, I get 16x squared minus 24x plus 9. So that's how I worked out the 3, because I was working out, okay, 2 lots of 12 is 24, that's what I want. Now, to work out how to factorize this, I actually use the answer that I've got here. So if I get the old highlighter out here, so this part here, 16x squared minus 24x plus 9, that's what I get if I normally expand this, but I don't want this, I want a plus 10 instead of plus 9. So what do I do to 9 to get to 10? Well, I just add on 1. So all I need to do here is just boo. Not with a highlighter, not to be recommended, but with a normal pen, we get plus 1. So our a and b are these values here. So a is equal to minus 3, and then b is equal to 1. And typical for these kind of questions, we're going to need that knowledge for the next part of the question. So it is given that the equation 16x squared minus 24x plus 10, so what we had before, is equal to k, where k is a constant, has exactly 1 root, which we'll come back to in a moment, and we need to find the value of that root. So with any quadratic, I always like the right-hand side to be 0. So I'm going to write down 16x squared minus 24x. I'm going to do a minus k on both sides here. So I get a plus 10 minus k is equal to 0. So all I've done to both sides, the original equation, is just minus k on both sides, so I get that right-hand side 0. Now, using the discriminant yet again, so exactly 1 root, so we're going to use that b squared minus 4ac from before, but this time, because we want exactly 1 root, we want to make it equal to 0 this time. These are really important facts to know. Again, our a, b, and c, like in the previous question, come from the coefficient of the a, the coefficient of the b, and then the constant term there as well. So let me just label this up for you so you can see which part is which. So this is a, this is b, and this is c. So we pop it into our formula. We then get minus 24 squared minus 4ac, so 4 times 16 times 10 minus k is equal to 0 this time. So again, we can use a calculator here. So I'm just going to do minus 24 squared very quickly. That's 576. Again, don't do that mentally. Minus 64 lots of 10 minus k is equal to 0. So we get 576 minus 640 plus 64k k is 0. 576 minus 640, that's equal to minus 64. Plus 64k is equal to 0. 64k is equal to 64. Therefore, k is equal to 1. It's very nice. When you get nice numbers, you know you're probably on the right track. However, this is not our final answer, so just be very careful with that. So notice if k is equal to 1, and we put it back in our normal quadratic, we get 16x squared minus 24x plus 10 is equal to 1. Therefore, 16x squared minus 24x plus 9, minusing 1 from both sides, is equal to 0. And we've seen that before in the previous question. If I go back, notice that 4x minus 3 all squared was equal to that expression. Therefore, we can say that 4x, sneaky, 4x minus 3 all squared is equal to 0, using that expansion I did in the first part of the question. And therefore, if we want to solve this, therefore 4x minus 3 must be equal to 0. Okay, you can square root both sides, and therefore x must be equal to 3 over 4, which is the actual root that we're looking for. So we're not looking for k here, we're actually looking for the root itself, which in this case is 3 over 4. Okay, you can check the solutions there as well, and you also get follow through marks if you don't get the correct answer for the first part of the question. Okay, and number 3 is trigonometric equations. Always a big topic on paper 1. So knowing your identities is really, really important, but also being able to problem solve, because there could be more than one way to get to the solution that you're looking for. Okay, and now we're going to look at trigonometric equations, which is a staple of the AS Maths paper 1. So you really do need to know how to manipulate these trigonometric equations and then solve them. So let's get started. So question 7a, and this is very typical. So we need to show that this expression here is equal to 2 over sine theta cos theta. And generally the way I go about doing this is I go, well, the left-hand side is equal to tan theta, and we're just going to copy this out here. So 1 plus cos theta plus tan theta over 1 minus cos theta. And our task is to make this look like the right-hand side. This is generally the approach that I take. And as soon as I have two fractions here, I always think about common denominators. And the first thing that comes to mind is actually multiply each by the other to actually get that common denominator. So what do I mean by that? Well, what I'm going to do is multiply these two things together. So that gives me 1 plus cosine theta multiplied by 1 minus cos theta. And then to work out the numerators, I times this by this and this by this. Again, very similar to how you multiply normal fractions. So if we do this, we get tan theta, open brackets, 1 minus cosine theta, and then plus tan theta. And we'll probably have to extend this divide line a little bit further, 1 plus cos theta. And now we're going to do some expanding. Now you may notice the bottom here of my fraction is actually a difference of 2 squares. So imagine I write this as 1 minus x, 1 plus x. Think of it in this way. If I multiply this out, I get 1, I get plus x minus x squared, and then these cancel, giving me 1 minus x squared. I can use this same quadratic technique to actually simplify this in the same way, which means I can go straight to 1 minus cos squared theta. So a little shortcut there that might save you those couple of minutes, that might save you the marks in the exam. Here at the top, however, we have a more straightforward multiplying out a single bracket. So tan theta times 1 is just tan theta. Tan theta times minus cos theta is just minus tan theta cos theta. Extend this again. And then here we just get plus tan theta and then plus tan theta cos theta. And something very nice has happened here. Well, we've got a plus tan theta cos theta, we have a minus tan theta cos theta, so these two things cancel, very helpful. And we get tan theta plus tan theta, which is 2 tan theta. Now, as I'm going along, I'm trying to simplify where I can. This can also be simplified, so 1 minus cos squared theta Remember the identity cosine squared theta plus sine squared theta is always equal to 1. So I can actually rearrange this to give you sine squared theta is always equal to 1 minus cosine squared theta. It's important to remember. So I'm going to just replace the bottom here with sine squared theta. At the moment, you might think we're not quite making the progress that we are hoping for. We've got 2, but this part at the bottom is not so clear. However, this says something also we need to know on the course is that tan theta is equal to sine theta over cos theta. So I can now replace the tan theta with sine over cos. That gives me 2 sine theta over cos theta sine squared theta. And now we have a cancellation of the sine thetas. So how many sine thetas go into sine theta? 1. How many sine thetas go into sine squared theta? Well, just sine theta. And we actually magically generate what we needed. So sine theta cos theta. And this is where I just state that this is equal to the right-hand side. So we have achieved our objective. We have made the left-hand side here look like the right-hand side. And what generally happens in these questions is that they use this identity to then lead into some solving. And this question is no different. So now we need to solve this very complicated looking equation. But now we know that the thing underlined here from what we literally just did is equal to 2 over sine theta cos theta. So using that, and this word hence gives us the clue we need to use it, we can actually just make this equal to then 6 over tan theta. Now at this point there's many different approaches you can take. I'm going to try a cross multiplying approach here. So I'm going to multiply this by this and this by this. If I do that, I get 2 tan theta is equal to 6 sine theta cos theta. At this point, I can change tan to sine over cos, like I did before, so 2 sine theta over cos theta. And again, there's no one correct way of doing this necessarily, but I'm just taking an approach and just trying to simplify as much as possible. So at this point, I'm going to times through by cos theta, so I get 2 sine theta is equal to 6 sine theta cos squared theta. I can cancel a sine theta from both sides here. That gives me 2 is equal to 6 cos squared theta. And now we're just working our way through, so we can divide by 6 here. So cos squared theta is equal to 2 over 6, which is equal to 1 over 3. At this point, I want to get cos on its own, or theta on its own, so I need to square root on both sides. That gives me then that cosine of theta is equal to, be very careful here, plus minus the square root of 1/3. And now to find our two answers, all we need to do is get rid of the cos. So what's the opposite of cosine? Inverse cosine on both sides. And notice the domain here is actually quite convenient for us. We only need to go between 0 and 180. So when we actually do this process, I'm just going to do now. So we're going to do the cosine inverse. And we'll take the plus version first, so the square root of the third. But don't forget, we've also got theta is equal to inverse cosine of minus the square root of a third as well. And now this is where finally we get to use our calculator and work it out. Okay, so I'm using my GDC here, but a normal calculator will be fine. So what we're going to do is take inverse cosine, and we're going to start with the positive version, so square root, and then we want the fraction button, 1 and 3. That gives us 54.7, and we're going to do exactly the same process now for the negative version, so minus square root 1 over 3, and that gives us the obtuse angle. So our final answers will be 54.7 and 125.3 to 1 decimal place. So let's pop that in. So we've got 54.7 degrees, 1 dp, 25.3 degrees, also to 1 decimal place. So you can check your answers there. It's exactly the same as what we've gone through. And this is where these videos are very helpful, because I take you directly through the method you need to solve these typical kind of trig equations. Okay, and on to our second example here. Again, very similar to how we approached the question before. So let's have a look at this. So we've got left-hand side is equal to 1 minus 2 sine squared theta over 1 minus sine squared theta. And the first thing I'm going to do here is use my identity. So 1 minus sine squared theta is equal to cosine squared theta. And as I'm doing this kind of problem, I'm thinking I want a tan at some point. I want to try and achieve that. So that's always in mind as I go through. Now, because I've got one thing in the denominator, I can actually separate this out. So 1 over cos squared theta minus 2 sine squared theta over cos squared theta. And at this point we can then change this slightly, so 1 over cos squared theta is the same as sec squared theta. So make sure you know this definition for sec and cosec. A sine squared over cos squared is equal to tan squared, so we get minus 2 tan squared theta. And we're almost there, so we just need to use another identity here, which is important. So sec squared theta is equal to 1 plus tan squared theta. Again, one to know really off by heart. It really does help you later on in the A-level course in general. And I'm going to substitute that in. And this is not the only way of solving this, but it seems a very convenient way because we can collect up like terms here. So 1 tan squared theta minus 2 tan squared theta is just minus tan squared theta, which is exactly what we wanted. So that is the right-hand side. And we have our answer like so. And here's the very typical part. So now we need to solve the equation using that identity from before. So we worked out the left-hand side was equal to 1 minus tan squared theta. So we're going to use and exploit that now. So let's work it out. So you get 1 minus tan squared theta is equal to 2 tan theta to the power of 4. And at this point, this doesn't actually look like something we can solve. However, first of all, I'm going to just write it in a slightly different way here and then show you what I'm up to. So I'm just going to bring everything to one side, which is a typical approach. Minus 1 is equal to 0. And now we're going to do a substitution. You've seen me do this trick in different parts of the video. I'm going to let y equal tan squared theta. And that means then y squared, if we square both sides, well, 2 times 2 is 4. So we get tan theta to the power of 4. And now we can just substitute this in. So we get 2y squared plus y minus 1 equal to 0. This factorizes nicely, so we get 2y and y there equals 0. Now we just need to think about where each of the numbers go. So we want a plus 1 here and a minus 1 there. Make sure it lines up nicely. And therefore y is equal to negative 1, or it's equal to a half. And therefore that means tan squared theta is equal to negative 1, or it's equal to a half. At this point, notice that if we tried to solve this, we'd actually get a complex number. So we can't actually solve this in the real sphere, so this answer won't work. But we can do this one. So tan squared theta is equal to a half, and therefore tan theta is equal to the square root, plus and minus, of course, of 1 over 2. So to find the final answers, we need to do theta is equal to tan inverse of the square root of a half and tan inverse of minus root of a half. This is where we go to our calculator and work out the answer. So we go to trig, and we're going to go tan inverse, and it's very similar to how we did the previous question. So we're going to write it in as 1 over 2. That's our first answer. And in fact, It's a very good thing you can actually do on this calculator. You can actually copy and paste. Isn't that cool? Again, this calculator is a little bit OP for this kind of question. And then we get this answer here as well. So notice this actually doesn't fit within the range that we wanted. We want between 0 and 180. So we just need the 35.3. And notice this was minus 35.3. So this way, you have to be careful with domain. This doesn't fit in the domain, but remember that it does repeat every 180 degrees. So if I take my minus 35.3 and add on 180, that will give me the solution within the correct domain. Because this is special for term because it repeats every 180. And if we do this, I'm going to do it on my calculator here, rather than go back to the other calculator. We then get 144.7. So just to make it very clear to the examiner, I'm going to put this in the box. So 35.3 is correct, and 144.7, like so. So again, you could have done this in radians as well. That's absolutely fine. But since this is in degrees, because notice the domain here is in degrees, that's why I've worked on degrees for this question. If you want to check the mark scheme, then have a look through here as well. And hopefully this gives you a good fundamental understanding of how to manipulate trig equations. Okay, and next is sequences and series, which is not too dissimilar from some of the iGCSE topics or AdMaths topics, but there's a little bit of trickiness involved as well, so make sure you're really good at getting those maximum marks on this kind of question. Okay, and let's get stuck into some sequences and series, typical on the AS Maths Cambridge course. So the first term of an arithmetic progression is equal to A, and the common difference here is minus 4. Now the first term of a geometric progression is going to be 5a, and the common ratio required is minus a quarter. And now we're told that the sum to infinity, so we're going to need to find that formula of the geometric progression. That's equal to the sum of the first 8 terms of the arithmetic progression. And we need to find the value of a. Very typical kind of question. So I'm going to start with the first part here, which is the sum to infinity of a geometric progression. So this is a formula that you need to know. So S infinity is equal to a over 1 minus r, where a represents the first term and r represents the common ratio. So if we substitute the a here for 5a and the r for minus a quarter and pop that in, we get then 5a over 1 minus a quarter. If we do a little bit of simplifying here, so we get 5a over, well, 1 plus a quarter, that's going to be equal to 5 over 4. And we can actually cancel 5 top and bottom, bring the 4 to the top, and then we're equal to 4a. So the sum to infinity is equal to 4a. And now we need to focus on the second part of the question, which is the sum of the first 8 terms of the arithmetic progression. This is equal to this 4a. So let's work out what S8 is first of all. This is also from the formula sheet. So the general formula, let me write that down first before we look at S8 in general. And this is a formula you need to know, is equal to n over 2, open brackets, 2a plus brackets n minus 1d. So I'm just taking this from the formula sheet directly, and we want to work out S8, where the first term is equal to a, so that won't change, and the common difference is equal to minus 4. So S8 will be equal to 8 over 2, remember n is equal to 8 here, open brackets, 2a, now d is equal to minus 4, so we get minus 4, open brackets, well, n is also equal to 8, so 8 minus 1. And let's simplify this down slightly, so 8 over 2 is equal to 4, 2a remains unchanged, and now if we work this out, so 8 minus 1 is 7, 7 times minus 4 is equal to minus 28. And once we've got that, we know that if I get a different colour pen here, let's get green, that this here, the 4a, is equal to what we've just worked out here. So at this point, we're now exploiting the fact that these two things are equal to each other. So therefore, we get 4 lots of 2a minus 28 is equal to 4a. And one of the reasons I didn't expand the bracket here is I can just simply cancel the 4 here and 4 here. Very nice. And then we get 2a minus 28 is equal to a, which we can rearrange here. And this then gives us a is equal to 28, like so. All I did here is a minus a on both sides and added 28 on both sides. And from that, we need to work out, well, the kth term of the arithmetic progression is 0. Find the value of k. Well, we now know that a is equal to 28. And if we look at the arithmetic progression, we know the common difference is equal to minus 4. So I'm just going to write that down, d equals minus 4. And we want to find the term such that it's equal to 0. Now remember, the nth term of arithmetic progression here is a plus brackets m minus 1d. So I'm going to exploit this. And I want to work out what it is equal to 0 and then find the term in which it gets to 0. So the way I'm going to do this is, well, a is 28. N is what I don't know, so we'll call that k here, looking for the kth term. And then we know d is equal to minus 4. And we want to work out when this is equal to 0. So once we have this expression, just using this formula over here, we're going to do some expanding and simplifying. So expand the bracket out, so minus 4 times k, well, that's equal to minus 4k. This is where to be very, very careful. So minus 4 times minus 1 is equal to plus 4, and that's equal to 0, like so. And now a little bit of rearrangement. So 28 plus 4, that's equal to 32, minus 4k is equal to 0. And now we power through the algebra, giving us then that k is equal to 8. Notice I'm going through these kind of processes quite quickly, because you should have that from the iGCSE or GCSE course that you've already completed. There's the mark scheme, so you can check exactly what I've done here and go through the working. I noticed with this AS Maths video that the mark schemes are not entirely helpful, so hopefully this video is helping you with this particular topic. Right, let's look at one more question like this. So the first term of arithmetic progression is 84. The common difference is minus 3. So a is equal to 84. D is equal to minus 3. And find the smallest value of n for which the nth term is negative. I'm going to take a similar approach to how I did the previous question. So I'm going to use the nth term formula, so a plus m minus 1d. And I'm going to set it equal to 0, and then I can adjust to see when it needs to be negative. You'll see this as we go through. So we'll take 84 as our first term. N is what we don't know at the moment, so we leave that alone. We know that d is equal to minus 3. And again, we're going to set this to 0 and see what we get. So we get 84, expand the bracket here, so minus 3 times n is minus 3n. Careful here, minus 1 times minus 3 is plus 3, which is equal to 0. 84 plus 3 is equal to 87. Plus 87 is equal to 0. So 3n is equal to 87. And now we have to divide here by 3. Now you have a calculator for this. I'm just going to do this old school. I do like a bit of old school maths. So 3's into 8 go 2, remainder 2. And then 3's into 27 go 9. So n is equal to 29. This is where we have to be very careful, because the 29th term is equal to 0, but we want to work out the next value such that the nth term is negative. So our actual answer here, and this is where we have to be very careful, is that we actually want n to be 30, because that will be the smallest negative number, minus 3. So imagine you've got your sequence, you've got 6, 3, 0, minus 3. This was the 29th term, and this is the 30th term, the smallest negative that is possible. So just be a little bit careful with those kinds of questions. Right, on to the next part of the question, and it is given that the sum of the first two k terms of this progression is equal to the sum of the first k terms, and we need to find the value of k. Okay, so we've got to just remind ourselves here, a is equal to 84, remember, of this progression, so what we used previously. D is equal to minus 3. And let's work out first of all the SK terms. So using the same formula as we did before here, so we get k over 2, and this is k here this time, open brackets, 2 lots of a, so 2 lots of 84, let me just write that as is, plus m minus 1d, so k minus 1 multiplied by minus 3. And let's simplify this down so it looks a little bit nicer. So we get k over 2, 2 lots of this is 168. Again, we've got a calculator for this. Minus 3k plus 3. And let's simplify this a little bit further. So k over 2. Then we get 171 minus 3k. And what we're going to do now is do exactly the same process for 2 lots of k. So we're going to substitute it in here. So we get 2k over 2. And then 2 lots of 84 doesn't change. This is still 168 plus, now we've got 2k minus 1 and minus 3 here. 2's cancel here, so we'll do this as we go along. So this is k. If we expand this out here, we still get 171 here. That hasn't changed. And this time we get a minus 6k. And what the question is saying here is that these two things are equal to each other. So let me underline that in green. So this expression here is equal to this expression here. So to finish this off. So therefore, k lots of 171 minus 6k is equal to k over 2, 171 minus 3k. Now, one of the reasons to keep it in bracketed form, that these two things cancel, saving us a bit of time here. So 171 minus 6k is equal to a half lots of 171 minus 3k. At this point, it's just using as efficient algebra as we can. I'm going to times both sides by 2 here, make our life a little bit easier. So we get 342 minus 12k is equal to 171 minus 3k. Subtract this from both sides, add 2k on. We get 171 is equal to 9k. I'm hoping this is where everything works nicely. So if we do this then, so k is equal to 171 divided by 9. This is where you hope you get a whole number out of it. So 9s into 1 don't go, 9s into 17 go 1 remainder 8, 9s into 81 go 9, so k is equal to 19. Again, feel free to use your calculator for these kinds of calculation as well. Right, so you can check the mark scheme. Again, not particularly helpful if you're studying this for the first time or really refreshing your knowledge of this topic, but hopefully my explanations have been clear here to help you through this particular topic.
And next is radian measure. So knowing what the radian is, that's obviously very useful, but then applying that to finding the area, finding various lengths and arcs as well. And that's an important topic. That also helps you later on in the A-level maths course, generally speaking.
Okay, and now we're going to look at some radian measure. So if this video has been useful to you so far, then do please think about liking and subscribing. Going a long way to supporting the content on the channel. Right, question 5. So in the diagram here, x and y are points on the line AB, such as BX, so this length here is equal to 9, and then we've got AY equaling 11. Arc BC is part of a circle with centre X, so this is our centre of the circle, and radius 9 centimeters, where CX is perpendicular to AB, so right angle here, and then arc AC is part of a circle with centre Y, so over here, and radius 11 centimeters. So the way to think about this problem is we have two sectors within this particular shape. So I'm going to draw this in red, just so you can see this nice and clearly. So we have this sector first of all. I'm just drawing round. I'm going to do something very similar in green here, so you can see the second sector as well. So we also have this sector where this is the centre, going down like so, and then we've got going round and upwards. So just keep this in mind as we go through this question, because that's going to be very important. Now the first thing we need to do is show the angle XYC. So if I mark that in, XYC. So this angle up here is equal to 0.5982 radians. So how do we show this? Well, we've actually got all the information that we need. So if we take the green sector here, well, this 11 centimeters is the radius, and this here YC is also going to be 11 centimeters because it's also a radius of the circle. So this is going to be 11 centimeters. Likewise, if you now look at the red sector, this here 9 centimeters is a radius. Therefore, this one down the bottom, XC, must also be 9 centimeters. And as soon as we see this, then we can simply use SOHCAHTOA to actually work out what we are looking for. So if I do this in blue. So we've got the angle here. This side here is opposite the angle. The 11 here is the hypotenuse. And then we think, okay, which of SOHCAHTOA includes both O and H? Well, it's going to be the first one. So it's going to be the SOH. So if we convert this now into what we need to do, so the sine of the angle, so sine of XYC is equal to, or opposite over hypotenuse, so 9 over 11. And therefore, to find the actual angle itself, what's the opposite of sine? Well, that's going to be sine inverse on both sides. So if we do this, this cancels, giving us XYC. And then we do the inverse sine of 9 over 11. So I'm going to go to the calculator now, make sure it is set in radians, that's really important, and let's work this out. So here's my trusty calculator. I'm going to use the Casio for this particular question, and all we need to do here is go to sine inverse, so shift and sine, open brackets. Notice this is already in radians at the top here, so it says rad. If you want to change it, you go to shift and setup, and now we just put in 9 divided by 11, just to verify everything that we've done here is correct. And we get 0.9582. So I'm just going to write that in. So 0.9582 dot dot dot. I'll put a little C for radians, and therefore this is correct. Now on to part B, which is a bit trickier. So you can see it's a 6-mark question here, is find the perimeter of ABC. So we need to find the perimeter of the entire shape. What we're going to start on first of all is the length of AB. So we're going to look at AB here. And something that could be very useful to us is actually working out what XY is here. So we're going to work out XY, and we can simply use Pythagoras because we've got the hypotenuse and a shorter side, and then we want to find the other shorter side. So if we use Pythagoras on this, then we know that XY squared, that's equal to the hypotenuse squared, 11 squared, minus 9 squared. And if we work through this, 11 squared is 121, 9 squared is equal to 81, and then if we take this away we get 40. So if we actually want to work out XY itself, what do we do to both sides? Well, we need to square root on both sides. So this length here is equal to the square root of 40. Now I'm going to keep this as precise as possible by leaving it in surd form so we can use that a bit later on. And this is very important for these kind of questions, not to be tempted to round too quickly. So if I use a different color, lots of colors in this particular question. So this yellow line representing XY, then this is equal to the square root of 40. So what we want to do now is we actually want to work out the length of AB. Well, let's think about this. So if we add 11 and 9 together, we do get 20. However, that includes this yellow length twice, essentially. We're sort of double counting it. So in order to work out AB, so let me get my red pen out here. To work out the length of AB, we need to add together the 11 and 9. But because we've double counted the yellow part, because we counted that twice, we need to take that away. So I'm going to minus the square root of 40. And I'm just going to keep that in this form, so 20 minus root 40. So we found the first part of our perimeter. Remember, the perimeter means the distance around the outside of the shape, and that is going to be equal to 20 minus root 40. Now actually, working out AC and BC is the easiest part here, and we need the arc formula using radians, which is really important. So to work out the arc, all we need to do is just r theta, where theta is in radians, which is really, really important. So if we do that for the first part, so let's work out AC here. So let's go over to here. AC, well, that's equal to r times theta. Well, r is equal to 11. And then the angle in terms of radians, we already worked out here, that's 0.9582. So I'm going to leave that like so. I'll work this out a little bit later on. To work out BC, it's a little bit different. So we need to use, first of all, use 9, because that's the radius. And be really careful here when using the formula. We do not want to put 90 degrees in. That's definitely a no-no. We need that in radians. So you need to know these exact values. So 90 degrees is the same as pi over 2 radians. The way I tend to work this out quickly is that I know 180 degrees is equal to pi radians, and I do all my conversions from there. So if I want 90 degrees, for example, what do I do to 180 to get to 90? Well, divide by 2. So I do the same to both sides. And so this helps me work out these exact values very, very quickly. So if we put this into the formula, we just get 9 times pi over 2. And to work out the perimeter, all I need to do is add all these things together. So I need to do 20 minus root 40 plus 11 times 0.9582 plus, and then 9 pi over 2. Only at this point would I actually then reach for my calculator, which I'm going to do now. Okay, so let's type this in nice and carefully. So open brackets, 20 minus, and we want square roots, that's shift in here. Try and use different calculators on the channel so you can see how each of them are used. And then we do 11 times 0.9582. And then lastly, we do 4.5 or 9 over 2 times pi. So shift and this button here. And then we add all those together and then we get our final answer of 38.352. So let's go back. 38.352 dot dot dot. Again, rounds to one decimal place at 38.4. Checking units here is equal to centimeters to 1 dp. And we've got all 6 marks. Right, so you can check the mark scheme there and just make sure that you've picked up all those method marks. Although it is a 6-mark question, notice you can pick up lots of those method marks as you go through logically through the problem. Right, and on to our second example, question 6. And we're not really going to use much of a calculator here in this particular question. So the diagram shows a metal plate ABC, which the sides are the straight line AB, and then you've got 2 arcs AC and BC. Line AB has length 6 centimeters. The arc AC is part of a circle with center B and radius 6 centimeters. Now what's actually quite useful to draw in here is if I draw in a dotted line just to show exactly where this arc is, and then BC also works in the same way with the center of A. So let me do that in a different color. So then we've got our center A also with the arc like so. And we need to first of all work out the perimeter of the plate. So again, very common asking you for the perimeter in these kind of questions. So what we essentially need to do here, if I put this in black, is work out the length of AC and work out the length of BC as well. So if we look at this particular question, notice that this 6 centimeters and this have to be the same. So this also needs to be 6 centimeters. And the other way around, so this is 6, because it's a radius, this is also a radius, this is also 6 centimeters. Therefore, we have a equilateral triangle. And the angles in an equilateral triangle, okay, each one is 60 degrees. Now, again, we're not working in degrees here, we are working in radians. Now, 60 degrees, that's equal to pi over 3 radians. And using the same technique that we saw earlier over here. So what do you do to 180 to get to 60? Divide by 3. So you can do it the same way here. So each of these angles is equal to pi over 3. Let's mark those in. And to work out the perimeter, well, first of all, we've got the 6. So don't forget the 6 at the bottom. And then we need to add on, using that formula for the arc, it's r theta. So that's 6 times pi over 3. And then we've got the other side, so that's also 6 times pi over 3. So again, I'm using this formula that I mentioned earlier. So arc is equal to r theta in radians. And we can just simplify this down. So we get 6 plus, well, these cancel, so we get 2 pi. We also get here 2 pi. And so we get our final answer of 6 plus 4 pi. Notice we're not reaching for the calculator because it says given your answer in terms of pi. So we want it left exactly like this. Okay, so just make sure you can see the answer there like so. And on to part B, which is a bit trickier here for 4 marks, is find the area of the plate. Again, not reaching for our calculator, giving your answer in terms of pi and root 3. Now we're going to use the other formula that's really important in AS Maths Paper 1, and that is the area of a sector. Again, it's worth remembering these off by heart actually, makes your life a bit quicker, and that's equal to a half r squared theta. Again, theta also being in radians. So I'm going to do a very similar technique to what we looked at before. So notice if I work out the area of the sector from A and the sector from B, notice we get that overlap of the triangle in the middle. So one way we can actually work this out, so the area of shape is 2 lots of the area of the sectors, and then minus the area of the triangle in the middle. Okay, so let's work out the area of one of the sectors. It's the same, obviously going both directions, so we can just times it by 2. So if we put that into our formula, we get a half times r squared, well, radius is equal to 6, and then times the angle, which is equal to pi over 3. And now we need to minus the area of the triangle. Okay, and here we need to use a formula you should be familiar with from iGCSE, but just in case we've forgotten, the area of a triangle is equal to a half AB sine C. So make sure you know this formula very, very well. And if we apply that here, so we get a half times A times B, so that's 6 times 6, the two sides, times the sine of the angle. Now, just being consistent here, if your calculator is in radians, angle in radians. If it's in degrees, in degrees. We're using radians here, so we're going to do pi over 3. Okay, so if then we just simplify this down a bit, so 2 times a half cancels, so that's good. So we get 36 pi over 3, which will simplify further later on. And if we look at this part, 6 times 6 is 36. 36 divided by 2 is 18. So we get 18 sine pi over 3. Now, let's just simplify this down a bit further and just think about this. So sine pi over 3, that's the same as sine 60. This is an exact value I'd really recommend you just to know off by heart. And I know that this is equal to root 3 over 2. If you want to know more about how I just know that, then do check out the video above where I go through how this is derived. Again, you can use your calculator on this as well. So let's simplify this down. So we have 36 divided by 3, that's equal to 12. So 12 pi. As I just told you here, this is equal to root 3 over 2. This is all good sign because we want it in terms of pi and root 3. And we're almost there, so now we get 12 pi. 18 divided by 2 is 9, so we get 9 root 3. You could factorize this further. I don't know if the mark scheme would want that. They're happy with exactly what I've left with, so that's good. But just notice here, you could also factorize this and show off the examiner a bit by taking a factor of 3 out and writing it like this too. That's also fine as well. Right, so you can have a look at the mark scheme. So you can see the first answer, 6 plus 4 pi, we got before, and also 6b. There are lots of different alternative methods here, so you may want to take one of those instead. I've kind of done it this way. I've taken this method, but this is almost identical to the top method here as well. So, hope you enjoyed the radian section of the video, and then we're going to move on.
And next is very specific to AS Maths Paper 1, and that is circle calculations. So we all know exactly what the equation of a circle is, but how do we actually use that in a coordinate geometry setting? And this is where a lot of your knowledge from other topics also come into play. Okay, and on to some circle calculations, an important topic on the AS Maths Paper 1. So, a circle with centre 5, 2, which is worth underlining here, passes through the point 7, 5. And we need to find the equation of the circle. Now remember, the general formula for the equation of the circle is equal to x minus a squared plus y minus b squared is equal to r squared. And this represents where the centre is equal to AB and the radius is equal to r. So we already have quite a bit of this information already. We know that a is equal to 5 and b is equal to 2 by using the formula, but now we need to work out what the radius is. And a quick sketch here really helps our understanding. So if I draw a quick sketch here, we have 5, 2, which is going to be the centre of our circle. Again, none of this is to scale. And we have the point 7, 5, which is going to be, say, up here somewhere. And imagine I draw a circle using this point here, so we go around like so. And what we're looking for essentially is the radius. So if I draw this in green, the radius, like so, we're looking for this length. Now we can actually use Pythagoras to work this out. Imagine I draw myself a right angle triangle. You can do it either way around. I'm going to draw it this way. So let's think, what do you do to 2 to get to 5? Well, that's going to be 3. And what do you do to 5 to get to 7? That's 2. So we can actually work out r squared directly by just using Pythagoras. So the length of the green line is equal to these two lengths squared. So 3 squared plus 2 squared. And if we do that, well, that's equal to 9 plus 4, which is equal to 13. So we get our value of r squared, which we need for our formula. So our answer is going to be the following. We're going to have x minus 5 all squared. Remember, the 5 comes from the centre of the circle, plus y minus 2 all squared. It comes from this 2 here, and this is equal to 13. Be careful, make sure it's not the square root of 13, but making sure you put down just 13, because we need r squared. Now, if we look at question B, the line y equals 5x minus 10 intersects the circle at A and B. So what does it actually look like? Well, imagine I get a line in blue here, having a y-intercept of minus 10, a very, very steep line because it's got a gradient of 5, and notice it crosses the circle twice, once here and once here, and we want to work out these two coordinates. And once you work those out, then we can use a similar method using Pythagoras to work out the length of the chord. So that's the theory. Let's get back into the practice. So first of all, I'm going to write down the equation of the circle. So x minus 5 all squared plus y minus 2 all squared is equal to 13. And we want this to intersect, so the y values are going to be the same. So wherever I see a y, let's get the old highlighter out. Wherever I see a y here, I'm going to replace it with 5x minus 10, keeping everything else the same. Now, I'm not going to do what I did before and use the highlighter. So let's just do this part now. So we get x minus 5 all squared plus, now y is equal to 5x minus 10, so 5x minus 10 minus 2 all squared is equal to 13. And let's expand some brackets. So x minus 5 all squared is going to be equal to x squared minus 10x plus 25. If you need to practice that, please do. It's a really important skill. Now, minus 10 minus 2 is equal to 5x minus 12. So we're going to need to expand that as well. So we get 25x squared. Minus 60x is minus 120x. Minus 12 times minus 12 is 144. Again, you can use your calculator to help you with these things. Now we're going to collect up the like terms. So 25x squared plus x squared, that's 26x squared. Minus 120x minus 10x is equal to minus 130x. And now we've got a little bit of calculation here to do. So 144 plus 25 is equal to 169. And now we just need to take the 13 away from both sides. And this is where we hope we get something quite nice coming out of this. So if we do this, we get 156 equals 0. So we've got a quadratic to solve. Now the first thing I'm going to do here is look at these coefficients and see if 26 goes into them. On the surface, 26 times 5 gives you 130, so that's good.
and it's an extra 26 there. So 26 times 6 is 156. So if you can always check these. So carry the 3, so 130. Again, you can use your calculator for this as well. So 6, carry the 3, 12, 156. So that's very helpful because we can take out a full factor of 26 out, leaving our quadratic being a bit easier to work with. So we get minus 5x plus 6 is equal to 0. And therefore, because you've got a constant term outside, we can ignore that because this has to be 0 in order to equal 0. So essentially, we just need to solve this very straightforward quadratic equals 0. If we do some factorising over here, we're going to get x minus 2, x minus 3 is equal to 0. So x is 2 and 3. This is why the iGCSE course and GCSE courses are very, very helpful. So you can do these very standard skills quite quickly. Now we actually need to work out what the actual coordinates are. Now you can substitute into both of these, either the circle or the straight line. The straight line is much easier to substitute into. So when x is 2, y is equal to 10 minus 10 is 0. Okay, that's nice and easy. And when x is equal to 3, y is equal to 15 minus 10, which is 5. So we've found our two coordinates. We have 2, 0, and we have 3, 5. So those are our two coordinates that we have. And at this point, all we need to use is the distance formula between these 2 points. So imagine this is your 2, 0. Imagine this is your 3, 5. All we're doing now is just using Pythagoras on this. You can do this a couple of different ways. So this would be 1, this would be 5. So the chord length will be equal to the square root of 5 squared plus 1 squared. Again, you can use the formula if you remember that, and that's equal to the square root of 26. Now notice they don't want a decimal here because in the question they say exact length. So as soon as they say exact length, you need to make sure you leave it as a surd. That's really, really important. Make sure you get all 7 marks. Big question, this one. Make sure you get all 7 marks on this question. Okay, so you can look through the mark scheme yourself and then just check my working and where you pick up those follow-through marks if you make some errors as you go through. Okay, and on to question 9. So a circle has centre at the point B, 5, 1, and the point A, minus 1, minus 2, lies on the circle. Very similar to how we did the previous question. We're going to still use that formula. What I'd recommend again is to draw a sketch. So making sure we understand exactly conceptually what's going on, because we're going to need this sketch anyway a little later on. So again, quick sketch, again, nothing to scale here. So 5, 1 is over here. Makes sense. And then minus 1, minus 2, that's going to be down here. So that's going to be our A. Let's just label these A and B. This is minus 1, minus 2. So we're going to get a circle that goes around this. So something that looks like this. Again, not to scale, this is not right in the center, but just to give us an idea of what's going on. So again, just like before, we need to work out r squared. So we need to work out this length here. The way we do this, because in black, is again use Pythagoras. I tend to do this visually. It's quite a nice way of explaining it. So minus 1 to 5, that's going to be 6. Minus 2 to 1, that's going to be 3. So r squared will equal just 6 squared plus 3 squared. That's equal to 36 plus 9, which is equal to 45. So now we use that formula. Remember the formula right at the back here, this formula here, and just substitute everything that I know. So our answer for 3 marks, that's kind of nice, is x minus 5 all squared plus y minus 1 all squared, and that's equal to 45, like so. But now we're going to have to use that diagram in a bit more detail. So point C is such that AC is the diameter of the circle, and point D, which is not on the circle, which is important to realise, has coordinates 5, 16. Show that DC is a tangent to the circle. So let's go back to my previous diagram and let's pop in this new point. I'll do this in red again. C. So it's over this side, and we don't know what it is, but we'll work it out in a moment. So we're going to work out this. So imagine this radius goes all the way through to give you a diameter. And there is a point D on the circle, which reminds ourselves is 516. So 516, that's going to be up here somewhere. This is D, 516. And what they're claiming is, and it kind of looks possible, is if I connect up D and C, that's a continuous line all the way through, that it's a tangent to the circle. So let's go through this one stage at a time. First of all, we need to work out C. Now notice that we went 6 along and 3 up to get to the radius, so we do the same thing again. We go 6 along and 3 up. So we do 5 plus 6, which gives us the 11, and then the 1 here, 1 plus 3 is equal to 4. So we see the same pattern, 6 and 3. Again, I can do it the other way round so you can see it. So this is 3 and this is 6 because they're both radiuses or radii, therefore need to be the same length. So we get C is equal to 11, 4. And we want to show it's a tangent to the circle, and therefore this means this is a right angle here. So in order to actually use the idea it's a right angle, we're going to work out the gradient of this line. So we're going to work out, and let's just write it over here, the gradient of the line AC. Or you can do BC as well, okay? So to work out the gradient, again, we use our formula. So y2 minus y1 over x2 minus x1, so the change in y over change in x. So if we do it here, we can take either way round to get 11. Okay, that goes on the bottom. Great. There we are. So we get 4 minus minus 2. Red pen colour, good. So 4 minus minus 2 divided by 11 minus, I think it's minus 1. Yeah, minus 1. So just comes from the coordinates. This gives us then 6 over 12, which is the same as a half. So the gradient of this diameter going across is a half. Therefore, if this is a right angle, then the gradient of this line has to be the negative reciprocal. Okay, what do I mean by that? So the gradient of CD, well, it needs to be this flipped and then changed to a negative. So if you flip this, we get 2 over 1, and then we change it to a negative, and therefore the gradient of that line is negative 2. So the gradient of this line is equal to negative 2. Therefore, we can write that line with the equation y equals minus 2x plus c, where at the moment we don't know what the y-intercept is, but we can work that out because c, which we already know, is actually on the line. So we can substitute that in. So when x is 11, y is equal to 4. So we get 4 is equal to minus 22 plus c, and therefore c is equal to 26. So this represents, I'll put this in the box, the equation of the line CD or DC, doesn't matter which way around. And now we check that point D works. So when x is equal to 5, y is equal to minus 10 plus 26, which is 16, which is good. So D is on the line. I think this is the easiest way to explain this question. There's plenty of other methods, but I like this one. You can use vectors as well. You can use Pythagoras a couple of times as well to also do this. Point C, so the other tangent from D to the circle touches the circle at E. Find the coordinates of E. So if we go back to our diagram. So imagine you've got a point over here. So this is our point E. If I draw this line here, which also just touches the circle. Now one thing to realize here is that this length and this length are exactly the same. So what I would do here, our diagram's getting a little bit messy at this point. Let's get the blue pen out. So if I do again another bit of Pythagoras or work out the gradient, these have to be the same. So what do I do to 11 to get to 5? Well, that's going to be 6. And what do I do to 4 to get to 16? That's 12. So it needs to stay on the same line. So the y-coordinate's not going to change, and I need to go 6 backwards. So 5 minus 6 is equal to minus 1. And it's still staying on the same line. So that's going to be equal to 4. So our answer, part E, which which is going to be the coordinates minus 1, 4. So utilising the idea that with two tangents from an edge of the circle, there we are, this picture here, that these lengths are the same. I've exploited this, so I know the y coordinate doesn't change, and the only thing that changes is x. In the same gap there is 5 to 11, it would be the same gap as well. And here are the answers for question 9, so you can check through everything that I've done here. Again, at 9b there are a ton of different methods you can use here. So you can think about this in terms of testing if Pythagoras works. That's one technique. You can also use, if you've done some work on vectors using scalar products, that also works very nicely as well.
And my next topic is functions. So again, a little bit of an upgrade from iGCSE. So you're having to work with domain and range a little bit more than you did at iGCSE, but also being able to find difficult inverses, which is also an important skill.
Okay, and on to some work on functions, which comes up very regularly on the AS Maths Paper 1. So the functions f and g are defined by the following. So f of x is equal to x squared plus 3, x is greater than 0, and g of x is equal to 2x plus 1, a nice linear function, if x is greater than minus a half. And the first thing we need to do is express f of g of x, so work out what f of g of x is. This is a very similar skill to GCSE and iGCSE. We work from right to left. So we're going to put g into f. Now, what do I mean by this? Well, let's get the trusty highlighter out here. So wherever we see an x in our f function, remember right to left, we're going to replace it with this entire 2x plus 1. Okay, let's have a look at what this actually looks like. So if we do this, we get the following. So we're going to get 2x plus 1 where the x was. Don't forget to square it, of course, and then we just add on 3. Now notice we don't need to expand this in any way. We can leave it as just an expression for f of g of x for the 1 mark over here. And now this is a typical follow-on question. We now need to find the inverse of what we just did. And we have a standard method for doing this. The first thing we do is we make y equal to the function. So 2x plus 1 all squared plus 3. Then we switch over the x's and y's. So we go x is equal to 2y plus 1 all squared plus 3. And now we have that longer process that we're going to do now, which is make y the subject, get y on its own. Now, how do we do this? Well, we just chip away at it one step at a time. So the plus 3 is kind of annoying near the y. So we do minus 3 on both sides. That gives us x minus 3 is equal to 2y plus 1 all squared. Now we can remove the squaring, because the opposite of squaring is square rooting on both sides. So we get the square root of x minus 3 is equal to 2y plus 1. And now just to make our life a little bit easier with the algebra, I'm going to flip over the equation so y is on the left-hand side. Makes it easier to deal with. Now we're going to minus 1 from both sides, making sure the minus 1 is separate to the square root. That's really important. And then the opposite of timesing by 2 is, of course, dividing by 2. So then we get the square root of x minus 3 minus 1 all over 2. And that is equal to the inverse that we were looking for. Now a quick comment about the domain of this particular function. Well, let's look at this very, very carefully. We're not allowed to have a negative square root. So notice here that x needs to be greater than 3. Now, one thing just to talk about here is why can't the domain be greater than or equal to 3? Well, if it's equal to 3, then we get a value of minus a half, which we're actually not allowed to have. So this is why x has to be greater than 3. Because we can't have negative square roots, and those things are generally quite bad. So our domain here is just x is greater than 3. Now on to the second part of the question, or part C, is to solve the equation. Again, this is very typical, so we're going to make another composite function, g of f of x, and then do some equation solving with it. Now a reminder, the f of g of x we worked out in part A, which is 2x plus 1 all squared plus 3. And with g of f of x, this works the other way round. So remember, we are working right to left, so always keep that in mind. So we're going to put f into g. So wherever I see an x in my g function, I'm going to replace it with x squared plus
3. Now if I do that, I get 2 lots of x squared plus 3 and plus 1, so let's get the plus 1 outside. And you can expand this so we can get 2x squared, well 3 times 2 is 6, and then plus 1 is the 7. And at this point we now just substitute into our equation. So f of g of x, we already know this, so this is 2x plus 1 all squared plus 3. Don't forget the minus 3, that's helpful, they're going to cancel, is equal to 2x squared plus 7. And we can expand out the bracket here, so remember you have to be really good at expanding your double brackets. So this is 4x squared plus 4x plus 1, but these cancel, equals 2x squared plus 7. And now it's just some standard quadratics here. So we're going to bring everything to the left-hand side. So we get 2x squared minus plus 4x and minus 6 equal to 0. We can take a factor of 2 out here to make our life a bit easier. So plus 2x minus 3 is equal to 0. So therefore we can ignore the 2 essentially at this point, because 2 times something is 0, so this must be equal to 0. And we're getting there. We're going to do a little bit of factorising now. Be careful with the solutions that we get. So we're going to have a plus 3 and a minus 1. Therefore our answers are x is equal to minus 3 and positive 1. And you think at this point, yes, I've got my answers, I can stop. But we need to be very careful because we go back to the domain of our function. X cannot be minus 3 because we're only looking for positive values and then greater than minus a half and 0. So therefore, minus 3 is not a solution here. This is a not acceptable solution. So our only answer here is the positive one, which is x is equal to 1. So just be very careful about working with the domain and range of functions at the end to make sure you've got the correct solution. Right, so you can have a look through the mark scheme so you can check everything there and making sure you get that accuracy mark at the end, just putting down x is equal to 1. Right, let's look at our second example of a function question. Again, this is very, very typical. So we've got a function here with a particular domain given, x is greater than a third. And the first thing we need to do is find an expression for the inverse. Works in the same way I did the previous question. So y is equal to 2x over 3x minus 1. We switch over the x's and y's. Notice we now get 2 lots of y here. So 2y here and a 3y at the bottom. And now this is a advanced but a standard procedure to actually find the inverse. First thing we're going to do is get rid of the fraction. So we're going to multiply both sides by 3y minus 1. If we do this, we get x lots of 3y minus 1 is equal to 2y. Expand the bracket out, so 3xy minus x is equal to 2y. And our general strategy here is put everything with y on the left-hand side, everything else on the right-hand side. So we get 3xy minus 2y is equal to x. And the reason we do this is a nice little sneaky trick to remember for the AS Maths Paper 1 is take out a factor of y. So we're going to put this into a single bracket, like so. Nice and sneaky. Make sure you put a 2 here and not a 1 like I just did, is equal to x, and therefore if we divide through by the bracket, we get y is equal to x over 3x minus 2, which is also equal to the inverse. So this is the nicest and tidiest way to actually put your function, so just having everything as positive as it can be, so plus x here and 3x here as well. And from there, we now need to do a little bit of algebra, and then we're going to work on what we just looked at in part C. So show that 2/3 plus this can be expressed as 2x over 3x minus 1. So looking at this, my first thought is, well, let's make the denominators the same. So I can take the 2/3 here, and I can times top and bottom by 3x minus 1. So that gives me 2 lots of 3x minus 1 over 3 lots of 3x minus 1. Now the reason I did this is now I've got a common denominator, so I can add these together. So 2 lots of 3x minus 1, 3 lots of 3x minus 1, plus 2 over 3 lots of 3x minus 1.
If I expand the top here, I get 6x minus 2 plus 2 over 3 lots of 3x minus 1. This cancels, very useful. So that's 6x over 3 lots of 3x minus 1. And don't forget there's a possibility of cancelling here because you've got a factor of 3 in top and bottom. So 3's into 3 go 1, 3's into 6 go 2, and then we get what we're looking for, which is 2x over 3x minus 1, like so. So we do get what we are looking for. And part C is really supposed to lead on from part B here, state the range of f. Because if you look at the function that we got, x over 3x minus 2, 2x over 3x minus 1, is kind of similar. However, the trick I always use here is that the range of f is the same as the domain of its inverse. So I always like to use this trick, using the idea of the inverse, the domain and range switching. So if we go back to our inverse function, so let's just write down our inverse function, which was from part A, so x over 3x minus 2. And what's the domain of this function? Well, the bottom is not allowed to be 0, and remember it's greater than a third. So if we look at our initial function here, it has to be greater than a third, therefore it needs to do the same situation at the bottom here. So the way I do this is just take 3x minus 2 is equal to 0 and solve this quickly. So x is 2/3, and then to fit in with the domain of the actual f function, x needs to be greater than 2/3 to be the range of the function. So this is generally the way I work out this. Try and stick everything into the domain and use the idea that the range of f is the same as the domain of its inverse. Right, so you can see the mark scheme there. Just be careful because I did put x is greater than 2/3. We need to change that into function notation. So f of x is greater than 2/3, or y, that's perfectly fine. So if you do use that trick, make sure you put f of x back in at the end. Everything else you can see there as well. So you can see the algebra that I've gone through as well. Again, make sure you revise this topic. This comes up pretty often, and it's one of the easier topics on the AS Maths Paper 1.
Okay, and on to two very big topics. The first one here being integration, so knowing how to integrate. And this comes up in two ways. You do a standard integration question where it just says integrate this and then work out plus c, but also the area between curves and lines, which I'm going to go through in quite a lot of detail.
Okay, and let's get stuck into some integration. And I'm looking at two specific kinds of questions here, which are very common in AS Maths Paper 1. So we're going to start with a standard integration problem, and then we're going to look at areas under curves or under lines, etc. So the equation of a curve is such that the dy by dx is equal to 1 over x minus 3 all squared plus x, and we're given that the curve passes through the point 2,7. That will become more important when we look at the constant of integration, and we need to find the equation of the curve. So whenever you see a fraction and you're looking to integrate, the first thing you need to be thinking of, works for differentiation as well, is change this into normal index form. So what do I mean by this? Well, we're going to do dy by dx, and we're just going to rewrite this as x minus 3 to the power of minus 2. So using those negative index laws that are very important when it comes to calculus. Now we have the derivative here and we want to work out the initial function, so we need to integrate both sides. So what we're going to do here is we're going to integrate on both sides. This has the effect of just giving us then y on this side, and on this side we need to do the integration here. So we're going to do the integral of x minus 3 to the power of minus 2 plus x with respect to x. Now, the way we actually do this integration, you'll find on paper 2 or paper 3 later on in the A-level course. It will become much more complicated. Here it is relatively straightforward. So to integrate this correctly, first of all, we need to increase the index by 1. So we go x minus 3 to the power of minus 1, and then divide through by the new index, which is minus 1.
Now, there is something called a chain rule where you actually have to take this into account and by inspection, but this has been set up specifically, so no chain rule is involved here. And if we integrate the x squared, well, we increase the index by 1, so increase that by 1 to 2, and then divide through by that new index, so over 2 like so. And of course, don't forget your constant of integration, so plus c for this kind of indefinite integration. We'll look at definite integration in the next question. Now we'll just tidy this up, so divide by minus 1, we can just bring this to the top, so we get minus, open brackets, minus 3 to the power of minus 1, plus a half x squared plus c. So this is much tidier. And like I hinted earlier, we need to use this point now, 2, 7, to work out the constant of integration. So when x is equal to 2, y is equal to 7, and now we just pop this in, so we get 7 equals minus, open brackets, 2 minus 3, to the power of minus 1, plus a half of 2 squared plus c. And if we work this out, so 2 minus 3 is minus 1, 2 minuses make a plus, so we get 7 equals 1, plus 2 plus c. And it's a really straightforward equation to solve, so c is equal to 4. So our final answer, so I'll put this in a quick box here, our final answer, so y is equal to, and we're just going to copy out the function, add in rc, so minus x minus 3 to the power of minus 1 plus a half x squared, and now don't forget this plus 4. That's why we used this point to work out exactly where the equation is. We found out the family of curves, and then we're looking for one particular solution. So you can check the answer scheme here. So this is the answer that we got. Again, or equivalent is fine, so if you rewrite this as a fraction, that is also okay as well. However, I would like to focus more on this kind of integration problem. As you can see, this is question 12 from a recent past paper. So these tend to end up towards the end of the paper and usually more on the tricky side. So the diagram shows a curve with equation y equals 4x to the power of a half minus 2x. If x is greater than 0, yep, you can see it's all to the right of the origin point, and a straight line with equation y equals 3 minus x, which we have there. The curve crosses the axis at 4, 0, which we're given, and crosses the straight line at B and C. And this is quite typical for an integration question. They'll get you to do some algebra first before we actually look at finding that shaded region. So find, by calculation, the x-coordinates of B and C. So notice B here and C here are where the line and this equation intersect. So therefore we need to find when they're equal to each other. So we make these expressions equal to each other. If we do that, we get 4x to the power of a half minus 2x is equal to 3 minus x. And now let's bring everything to one side. So we're going to add x on both sides and minus 3 on both sides. So we can get it in that typical quadratic fashion that we like. So we get 4x to the power of a half minus x. So I'm just double checking everything here. And minus 3 is equal to 0. And this doesn't look like a very particularly nice equation to work with here. In fact, I'm going to do a little bit of moving things around. So what I'm going to do first of all is times by minus 1. And you'll see why a bit later on. So plus x and plus 3 is equal to 0. And then rearrange this to put the x at the front. So again, you're going to see why this is the case. Half plus 3 is equal to 0. Now we're going to do a very nice substitution. So I'm going to put this up here. So let y equal x to the power of a half. This is a very standard technique. It also works with general exponential equations and logarithmic equations. And all I'm going to do here is square on both sides. If I square on both sides, well, I get y squared on the left-hand side. If I square this, well, half times 2 is equal to 1. So y squared is equal to x. So if I use this very nice substitution here, if I replace my x with a y squared, and I replace my x power of a half with y, notice we essentially get a very nice quadratic equation falling out. And we know how to solve these from earlier parts of this particular video. So we go to y, and y is equal to 0, so we're going to factorize. So we're going to have minus 1 and minus 3. Therefore, our answers are y equals 1 and 3. And now we go back into this substitution. So we're going to replace the y with x to the power of a half. So that means x to the power of a half is equal to 1 or 3. And in order to get x on its own, we square both sides. And that will give us our x coordinate. This cancels. We get x is equal to, well, 1 squared is equal to 1. And then 3 squared is equal to 9. So this helps us work out that this is going to be 9 something. We're going to work out something a bit later on. And then the b here is going to be 1 something, which we could work out by substituting into the straight line. So our two final answers here, x equals to 1 and x is equal to 9. Now on to part b, which is showing that b is a stationary point on the curve. Okay, so we know that b, the x coordinate of it, from what we just did here, is 1 something. Something doesn't really matter here. We want to work out a stationary point, and this is typical for calculus questions generally. There might be some differentiation involved as well. So let's write down our curve, because that's what we're looking at here. So y is equal to 4x to the power of a half minus 2x. And as soon as you see stationary points, there's always a clear procedure you do here. First of all, we want to differentiate, so find dy by dx. The way that we do this, as a reminder for you, you'll see this in the differentiation part as well, is we do a half times 4, which gives you 2, like so. And then we reduce the index by 1, so we get x to the power of minus a half. Likewise here, if we differentiate here, we just get the number in front of the x, so we just get minus 2, like so. And we want to check it's a stationary point, this one here. So let's put in x equals 1 and see what happens. So when x is equal to 1, dy by dx is equal to 2 lots of 1 power of minus a half minus 2. Well, 1's power of anything is just 1. So that gives us 2. 2 times 1 is 2. Minus 2 is 0. And because dy by dx is equal to 0, that means it must be a stationary point. Stationary with an A here, not with an E. So whenever you see stationary point, you need to be thinking dy by dx is 0 and working your way towards that. That's very, very important. Okay, the trickiest part of the question is finding the area of the shaded region, and we're giving 6 marks for this particular part of the question, and we're going to need to use the diagram so we can represent visually what is going on. So the way we do this is by working out 2 separate areas. The first area that we're actually going to represent is the triangle. Now, you're probably saying, there is no triangle on the board, Mr. Gower. Where is this triangle? Well, let me pop this in first of all. Imagine you draw a triangle in. I'm going to do this in green, like so. So this right angle triangle. Now we actually do know these points. We can work these out pretty straightforwardly. First of all, this is 3 minus x. So when y is equal to 0, then x needs to be equal to 3. So we know this is at 3. We know this is at 9 here, because it's the same as this one down here. And also very important for this question, we also need to work out the y value. We can do this by just putting in 9 into the straight line equation. Probably the easiest thing to do. And that gives us minus 6. So we have minus 6 down here. And essentially, we've got a triangle. So imagine I zoom this out. We've got a triangle here. This is the right-angled one. Well, the difference between 3 and 9, that's 6. Difference between 0, so the x-axis, and minus 6 is just 6. And we can work out the area of this triangle very, very easily. So the area of the triangle, which we'll come back to, is a half of 6 times 6, which is equal to 18. So we're going to keep that in mind, and you're going to see what I'm going to do in the next part of the question. So we worked out the area of the whole triangle. What we're now going to do is use integration. Let's use a different colour, let's use blue. So we've got this point here, 4, this is 9, and we're going to use integration to actually work out the area below the curve. So we're going to work out this particular area here, the one in blue. And you can probably see what we're heading towards here. We're going to take the green area away from the blue, and that will give us this very small area here. So we want to find the area under the curve, so we're going to have to use some integration. We already have the limits, which is very useful. So 4 and 9, and of course the curve from before. So
in order to work out the area of the blue, so I'm going to put area of blue, so I can just indicate to the examiner what I'm looking for. It's going to be the following integral, so it's going to be the integral between 9 and 4, looking for the area under the curve of our function from before, so 4x to the power of a half minus 2x with respect to x. Now, integration, remember, you need to be very clear in your mind. If you're doing integration, differentiation, we are integrating here. So remember the process. We add 1 to the index, so we get 4x to the power of 3 over 2, and then divide by that index. So divide by 3 over 2. We'll tidy that up in a moment. Same here. So we get 2x squared, and then we divide by that index. And we're doing this between 9 and 4. Let's tidy this up before we continue our integration. So if we actually just flip this in times, that's going to give us 8 over 3 x to the power of 3 over 2 minus, well, okay, just cancel, so x squared between 9 and 4. And now we're actually going to work this out by substituting 9 in first and then minusing, substituting 4 in. You'll see what I mean as we go through. So we're going to do 8 over 3, 9 to the power of 3 over 2 minus 9 squared, minus, and now we do exactly the same process, just put 4 in instead, so 8 over 3, 4 to the power of 3 over 2 minus 16. And all we need to do is work this part out at this point. So square root of 9 is 3, 27. 27, that cancels, so that gives us 72. So 72 minus 81. Minus, and square root of 4 is 2. 2 cubed is 8. That's 64 over 3. And you can use your calculator to help you here. Minus 16. And let's just pop up the answer over here. So 72 minus 81, that's going to give us negative 9. And it should be negative because we're finding an area below the x-axis. And if we work out 64 over 3 minus 16, that's going to be equal to minus 5/3. Again, you can use your calculator, and that's going to be equal to minus 14 1/3. So to work out our very, very final answer here, so let's put it over here, we're going to take the area of the triangle, which is the bigger area, and then take away the area of that smaller area in blue. And if we find the difference between that, so 18 minus 14/3, we'll then get to our answer of 3 2/3, which will be our final answer. Again, you can check my working here. Again, working out that shaded region. And this is pretty much as difficult as it gets in terms of integration on the course. So just be aware, you'll be expected to do your standard integrals, but you'll also be expected to work out the area below the curve or between a curve and a line, etc. And I've taken one of the very hardest examples here as well. Again, you can have a look through the answers. There's alternative methods there for you as well, if you prefer. And also what I did just at the end.
And our next topic is differentiation. If we've done integration, I'm probably going to do differentiation as well. And making sure you're really familiar with the chain rule and using that in a practical context, but also using differentiation to find the nature of stationary points too.
Okay, and on to a fundamental part of the course, which is, of course, differentiation, being able to use the chain rule, making sure that we're happy with that, and also different style of questions. So the equation of the curve is given as 2 plus the square root of 25 minus x squared, and we need to find the coordinates of the point of the curve at which the gradient is 4/3. So as soon as you see a function and you see gradient is equal to something, you need to be thinking differentiation. So use that as a trigger to go for the right process. So first of all, I'm going to write this slightly differently. So whenever you work with calculus, so differentiation or integration, you tend to want to write this in index notation. So remember, the square root of something is the same as 2 to the power of a half. And that's going to help us with using the chain rule in the very next step. Now, we want to find the derivative of this. So the way we do this is we're going to go dy by dx. Now, if you derive 2, you're going to get 0, so that disappears completely.
And now we're going to find the derivative of this. So this takes a little bit more concentration here. First of all, we're going to take the half and bring it to the front. So we get 1/2 here. Then we're going to multiply by the derivative of this in the bracket. So if we derive what's inside the bracket, that gives you, well, 25 goes to 0, and minus x squared, that's going to become minus 2x, like so. And then we copy across the bracket, so that stays the same, and then reduce the index by 1. So 1/2 minus 1 gives you then minus 1/2. Now we're going to do a little bit of tidying up here. So first of all, 1/2 times minus 2x gives us just minus x, which is very helpful. And then we have the 25 minus x squared to the power of negative 1/2. And again, we can convert this back into this kind of original form. Remember, minus 1/2 means it needs to go on the bottom. So we get minus x on the top, and then we get the square root of 25 minus x squared on the bottom. And that's what dy by dx is equal to. Now we need to work out the coordinates of the point where the gradient is equal to 4/3. So we want to make this equal to 4/3. And probably the easiest way of working with this equation is we don't like the square root. That kind of irritates us. So we're going to square everything here to ensure that that disappears. So if we do that, if we square the top, minus x times minus x is just x squared. This stays as is, so the square root disappears, 25 minus x squared. And if we square this fraction here, well, 4 times 4 is 16, and this is equal to 9. Now this suddenly turns into something that we can certainly work with at this point. We're going to do our favourite process, which is, of course, cross-multiplying, like so. So if we cross-multiply here, I'm going to continue this over here. Then we get 16 lots of 25 minus x squared, and that's equal to 9x squared. And now it's a case of a little bit of expansion here and working our way through. So if we do 25 times 16, we get 400. So we're going to get 400 minus 16x squared is equal to 9x squared. That means then that 25x squared is equal to 400. This is looking already very, very nice, which is always good. So that means then that x squared is equal to 16. Remember, 400 divided by 25 is 16. And so x is equal to plus or minus 4. Now, it doesn't actually matter which one we take to work out the y-coordinate. Notice when we substitute x back into the original equation that it's going to be squared anyway. So when x is equal to minus 4 or 4, y is going to be equal to, we're just going to copy this out here and replace the x with a 4 or minus 4. It makes no difference. So we get 25, well, 4 squared is 16. So we get 2 plus the square root of 9. And this is going to equal 5. So our final answer here, let me pop this just down over here. Our coordinate is going to be minus 4, 5. It could also be 4, 5 as well. I think, remember the mark scheme, it's minus 4, 5 here. Yeah, they take this one here instead. But notice you can take both and it still generates exactly the same answer. Okay, so there's the mark scheme. Do have a look through it and make sure you're happy with where the B marks are, the M1 marks are, and the 2 A1 marks at the end. Right, let's move on to a slightly different style of question here with question 9. So the equation of the curve is equal to y equals 3 minus 2x all cubed plus 24x. And the first is we need to find the first and second derivative here. Okay, so let's start with the first derivative. So we have to be very careful with our chain rule. So the first thing we're going to do here is going to bring 3 to the front when we're differentiating. So 3. Now multiplied by the derivative of what's inside the bracket. Well, minus 2x, if you find the derivative of that, is just minus 2. Then we just copy over the bracket, so 3 minus 2x, and then reduce the index by 1. So that gives us to the power of 2. And if we derive 24x, it's always nice when there's no, it's just x to the power of 1, then that just becomes 24. And we can tidy this up somewhat, so we tidy this up. 3 times minus 2 is minus 6, and we can leave everything else the same. So that's our first derivative.
dy by dx is equal to this. And if we work out now d2y over dx squared, well, we're just going to find the derivative of what we've just found. So we do this in exactly the same way. We take the 2 and bring it to the front. So we're going to get minus 6 times 2. The derivative of what's inside the bracket is all again equal to minus 2. We reduce the index by 1. Once we copy that the brackets, that stays as 3 minus 2x. And if we find the derivative of a number, that just disappears. So if we tidy this up again, so minus 6 times 2 is minus 12, times minus 2 is positive 24. Careful with the two minuses. And then we get our second derivative, which is what we're looking for. So again, if you need to go through that step again, so using the chain rule, and then please do. I've gone through it fairly quickly. I'm trying to limit this video to about 2 hours in total, so I'm going through these topics fairly quickly. On to part B, find the coordinates of each of the stationary points on the curve. So this is a key thing. As soon as you see stationary points, the thing to remember here is that dy by dx needs to be equal to 0. So as soon as you see that phrase, stationary points, think dy by dx is 0. Actually, instant thing that you think of. So if I copy that across from before, so we had minus 6, 3 minus 2x all squared plus 24. So that's going to be equal to 0. And now we just solve the equation. Again, don't rush to expand brackets here, and you'll see why. So we're going to minus 24 from both sides. That gives us minus 6, 3 minus 2x all squared is equal to minus 24. Now we're just going to divide by the minus 6 on both sides. So that gives us 3 minus 2x all squared is equal to positive 4. Now you probably see why we didn't actually expand the bracket out, because we can actually square root both sides here. It's a very nice way of getting to the answer. It's already in factorized form. So square rooting this side here, we'll just cancel here. So we'll get 3 minus 2x. Now be a bit careful when you are square rooting 4, because you're going to get plus and minus 2. So you need to keep that in mind. And from here we can actually solve kind of simultaneously to actually work out the two different answers for x. So I'm going to minus 3 from both sides. So I get plus minus 2 minus 3. That means then that minus 2x is equal to either, at this point, either minus 1 or minus 5. Therefore, we can times through by minus 1, giving us 2x is equal to 1 or 5. And therefore, x is going to be equal to 0.5 or 2.5. So we get the x coordinates, but of course it wants the full coordinates here for these stationary points. So what we're going to do is going to substitute it back in. So when x is equal to 0.5, we're going to put this back in. So y is equal to bracket 3 minus 2 lots of 0.5. And it's just being very careful here, making sure no silly errors creep in. Plus 24 lots of 0.5. So we get 2 times that's 1. So we get 8 plus 12, which is equal to 20. And now we do the same thing for 2.5. So we get y is equal to 3 minus 2 lots of 2.5 cubed plus 24 lots 2.5. If we work through this, so we get, this is 5 minus 2 cubed, that's equal to minus 8. I do 48 plus 12, that's 60. So I'm getting the answer here of 52. So just making sure it's nice and clear for the examiner. Answers are 0.5 and 20, and then 2.5 and 52. So these are our two stationary points or turning points. And in the last part of the question here, we're actually going to determine the nature of each stationary point. As soon as you see this phrase, so nature of each stationary point, we want to work out whether it's a maximum, a minimum, or a point of inflection. And I'll explain how we work this out using something that we did in part A. So we're going to need d2y over dx squared. So I'm going to write this down just again. This is how the classical way of working out what these stationary points do. And we're just going to substitute in the x coordinates of both here.
0.5 and 2.5 and see what comes out. So when x is equal to 0.5, d2y over dx squared, 24 lots of 3 minus 2 lots, 0.5, and that's going to give us 48. Now because this is a positive number, so this d2y of dx squared is a positive number, that means it's going to be a minimum. And we do exactly the same process with 2.5, so we're going to work out what d2y over dx squared is equal to. So 24 lots of 3 minus 2 lots of 2.5. You can probably see where this is going. So we get 24 times minus 2 minus 48. Well, this is negative and therefore must be a maximum. Now just to clarify for the examiner, what I would write here very, very clearly is I'm going to write this is a minimum, just in case you don't understand my working, and then 2.5 and 52, and that's going to be a maximum. Just so there is no problem here, we've made it very, very clear what nature each of those stationary points have. So you can check the mark scheme, you can see exactly where I'm picking up those base marks, those method marks, and also those accuracy marks as well.
And our very last topic, which comes up pretty much every year in some shape or form, is transformation of graphs. So knowing how to use function notation to describe a reflection or a translation, and also working backwards. This can also involve sinusoidal modelling, and you're going to see all of that in the next two questions.
Okay, and on to probably the smallest section of this particular video, but an important one as well. So you really need to know how to work with transformations of graphs. It's quite hard to go through every single kind of question, but I've tried to pick out a couple here that are really sort of standard ideas that you need to understand. So number 4, the diagram shows the graph of y equals f of x, so we're not told what the function is. Where f of x, oh, we are told what the function is equal to 3 over 2 cos 2x plus a half, and the domain is between 0 and pi. And now we need to state the range of f. So the way I approach this particular sinusoidal model is I would look at the cos x here specifically and think about, okay, if you take a cos function, what are the maximum and minimum values? So for any cos functions, let's just say cos theta, the maximum it can be is +1, and the minimum it can be is -1. So these are the maximum minimums for this function, and what I now do is just substitute that into this particular function and then work out what the maximum for the function is. So what do I mean by this? So when cos x, 2x, sorry, is equal to, say, 1, then that means that f of x is equal to 3 over 2 lots of 1 plus a half, and that gives me positive 2. And when cos x is the very most negative it can be, so -1, then f of x is equal to 3 over 2 minus 1 plus a half. This works really well with sinusoidal functions, so sine and cosine. And if we work this out, we get -3 over 2 plus a half, giving us -1. So our range here of the function, so what can y be, is simply these values. So -1 is less than or equal to the function, which is less than or equal to 2. If you look at the graph, that makes a lot of sense. So if you look at this, this looks around about 2, this looks around about -1. So this also fits in with the diagram that we have in front of us. 4b, so this is a little bit trickier. So the function g is such that g of x is equal to f of x plus k, where k is a positive constant, and the x-axis is now a tangent to the curve y equals g of x. So when they say that, what they mean is, say I've got my x-axis here, then my function just touches the axis and then goes up like so. So that's what they mean by this tangent to the curve phrase. Now also notice here, with f of x plus k, the k, what impact this has, this is a translation upwards or downwards. So we're going to combine all that knowledge together to then work out what the value of k is and then describe fully the transformations. So we want this effect to happen, and we can move by a translation upwards or downwards. So if we go to this feature here, notice the range of our function. This helps us a lot here. The y value is equal to -1, so here. And what we want essentially for this to do is go up to here. So that's what we want. So we want a translation that basically moves this 1 unit upwards. Now in order to achieve that, then what we need to do here is work out that k must be equal to 1, because adding 1 to the function basically has a vertical shift going 1 upwards, so it will come to here, which is what we want. And the transformation that we want is a translation 1 unit, which is very important, and this is a vertically upwards. So again, 2-mark question, so 2 bits of information. K is 1, the first part, and then the transformation that's happened. Now we need to state the equation of the curve, which is the reflection of y equals f of x in the x-axis. That's really important. And reflection. Give your answer in the form y equals a cos 2x plus ab, a constant. Right, so whenever you have a reflection, and these are ones you need to learn off by heart, not generally given to you, an x-axis, then the function is generally written as minus f of x. And I'll talk about the reflection of the y-axis in the very next question. So all we need to do is just do minus f of x. Well, f of x is equal to this. So all we need to do is put a minus in front of the entire function. So 3 over 2 cos 2x plus a half. And if we multiply out the single bracket, then we get y is equal to minus 3 over 2 cosine 2x minus a half. Remember, both of these turn negative in order to get this reflection happening. So a is equal to minus 3 over 2 and b is equal to minus a half. Again, you can check the mark scheme there. It's not very helpful explaining exactly where these answers come from. This is why I make these exact videos, to help you really understand what's going on with these kind of questions. Right, on to question 3. Notice a lot of these transformation style questions are towards the start of the paper, so generally on the easier side. So, in each parts A, B and C, the graph shown with solid lines has equation y equals f of x, and the graph shown with broken lines, so this over here, is a transformation. So we want to go from here to here, and then we need to write, in terms of f, the equation of the graph shown with broken lines. So the first thing to do here is recognize the transformation. Notice we have a reflection here, but different to our previous question, it's in the y-axis. So remember, when it was a transformation in the x-axis, it was minus f of x. If it's a transformation, a reflection in the y-axis, then it's equal to f of minus x. So where the minus goes is very, very important. And now we've got a stretch going on here. So we want to go from this function to this function. Notice it's a stretch. Now, how do I recognize this? Well, if you look going in the y direction, nothing really changes, but the x it certainly does. So, for example, we start with a function going from here to here, so that's 2, and if I use a different color and go then to our new function, that's going to be equal to 4. So notice there is a doubling effect going on here, meaning it stretches in the y direction. Notice my arrow points upwards, so y direction. Now that makes our stretch a little bit easier to write. So whenever it's stretching, so this is a stretch factor 2 in the y direction, then we'd write this as 2f of x. Now if this is a stretch in the x direction, we have to be really, really careful with the scale factor 2, because then it'll be f of half of x. But again, that's something you'll need to look up. In this case, this is quite an easy one to write down, just 2f of x. And the last part here, so this is a bit trickier. So state in terms of f the equation of the graph. Notice here it's a translation, so it's a movement of the shape. So that's really, really important. And let's see how far we're moving. So let's take a corresponding point. So if we go across here, we're going 4 units to the left, and we're going 3 units down. So our translation would be, in vector notation, -4 and then -3. Now putting this into function notation, you have to be really, really careful with this one, so the x and y, because it does the opposite of what you expect inside the bracket. So when we write this in, we're going to put an x plus 4. Now notice it is a -4 with our bracket, but because we're working with the x-axis, it does the opposite of what we expect, whereas with the y, it does what we expect. So this will be -3. Again, these are rules, particularly transformation of graphs, you need to learn off by heart, recognizing even though our vector is -4, -3, whenever something's inside the bracket, it does the opposite of what you expect. You expect this to be a -4, because inside the bracket it's a +4, but if it's outside the bracket, it does what you expect, which is -3. So just be very careful with these kinds of transformation of graphs questions. Okay, so you can check the mark scheme again for those 3 questions. Again, pretty straightforward questions, but you really do need to know your transformations of graphs really, really well. This is a topic I often find students struggle with, so make sure you really revise this because it's one of my certain topics that often appear on the AS Maths Paper 1.
Okay, so I hope you enjoyed this series of the top 10 topics you need to know for AS Maths Paper 1. If you like the video, of course, then please do give it a like and think about subscribing to the channel, because if you like this kind of content, I'm more than happy to looking at Paper 2 or Paper 3 or the mechanics and stats as well. I'm more than happy to have a look. And if you're looking for more practice, generally speaking, on getting into the right mental state for the exams, then please do check out the video just over here, not over here, but over here.